Alright guys, we're going to go over Study Guide Unit 17 for Conceptual Chemistry. So for question number 1, it says, what two conditions are necessary for a chemical reaction to occur? So really there are two conditions that describe one event. So you need a collision, and then that collision needs to have enough energy, so they got to hit hard enough, and we call that the E of A, or the activation energy. And then the other thing that you need is you need the collision to have the correct orientation. So the two reactants need to not only collide, but they need to collide in the correct way. Orientation. Okay. Then we've got list the 5 ways to increase the rate of the reaction. So we can, and we're increasing the rate. So we're going to increase concentration. We can agitate, we can shake it up or stir it. Agitate. We can increase surface area. We can increase heat. Really, like when we say heat, meaning temp, okay, because we want to change the kinetic value, the amount of motion, by changing the temperature in Kelvin. And then the final thing is we can use a catalyst. My pen is dying, so I'm going to switch over to a black pen. Okay. So question 2 or 3 rather says, how does a catalyst work? So catalysts work by the way that what they do is they're going to increase the rates by decreasing the E of A, the energy of activation required, by helping form the orientation. So in other words, they're going to help the two reactants get together in the right shape so that it's not going to take as much energy for the reaction to occur. Okay? And so what is activation energy? It's the energy required for the reaction to occur. Okay, so in other words, it's the starting value. In order to get through the reaction, in order to get the products, you have to pay this amount. Every reaction has an activation energy. All right, so number 5, on the graphs below, draw exothermic reaction and an endothermic reaction. So let's start with exo. So this is going to be our exothermic reaction. And we also need to use a dashed line to show a catalyst being added. So you always start with your reactant. Here's my R for my reactant. Must see R, but whatever. Then we have our hill. We always have a hill at the beginning of a reaction because we have to pay our E of A, our energy of activation. And then this is an exothermic reaction, which means over the course of the reaction, heat is going to be released. So our products are going to have a lower energy than our reactant did. So these are our products. Okay. And then they want us to draw a dashed line to show a catalyst being added. So catalysts lower the E of A. Another way of saying that is they lower this hill, the cost. So if I don't use a catalyst, I will have to pay this much energy. Okay, so this is the normal E of A. And then this distance here, that's the E of A with a catalyst. Okay, so you only have to pay this much versus the whole thing. Okay, let's draw our endothermic reaction. So same deal. You always start with your reactant. Much better R, right? A lot prettier. You have your E of A. But in this case, it's endothermic, which means energy is going to be absorbed from reactant to product. So when we come down, we don't come down as far. The products need to end up with more energy, right? And the y-axis measures energy. So if the reactants had this much energy, the products need to be somewhere up here. So I'm going to put them right here to show that the products have more energy than the reactants did. Okay. Number 6. What does it mean for a reaction to be reversible? Essentially, that products can react to reform reactants. So in other words, you can make your you can use your reactants to make your products, but your products can then react to turn back into the reactants. On the chemical equation below, for number 7, draw and label the forward and reverse reaction. So I think just looking for that. Yeah, so that way is going to be the forward reaction, and that way is going to be the reverse reaction. But the way that you show it's reversible is by using this double arrow here. Okay. For number 8, describe the rate of a reaction when it's at equilibrium. The forward rate equals the reverse rate. Okay, so in other words, if we go back up here, the rate at which we are turning A and B into C and D is equal to the rate at which C and D are being turned into A and B. I described this earlier to some students as if I am making sandwiches. So I have bread, I have cheese, okay, slices of cheese, and then I have some salami, right? And I'm turning that into sandwiches, right? So if I start doing this, and let's say I make 3 sandwiches a minute, okay, and I have 9 sandwiches. But then my wife comes along and she says, oh, we don't need sandwiches. I'm going to take these apart and put them back in the refrigerator. And she does it at 3 minutes, 3 sandwiches a minute as well. Then nothing will ever change, meaning the amount of ingredients that I have won't change, and the amount of sandwiches we have will not change, because as I make 3, she's going to unmake 3. Okay, that doesn't matter how much is on either side. If I only had enough to make 1 sandwich left over here, so I literally have 2 pieces of bread, 1 meat, 1 cheese, okay, I'll have 9 sandwiches over here, but the fact is it's not the amounts that are equal, because I only have enough to make 1 sandwich versus having 9 sandwiches. The fact is at equilibrium, we make sandwiches as fast as we unmake sandwiches. So the amounts on either side never change, but they don't have to be equal. The only thing that has to be equal is the rate in the middle. Okay, so the forward rate equals the reverse rate. And then the last thing on front page is summarize Le Chatelier's principle in your own words. So essentially, if you stress an equilibrium, I'm going to put EQ for, we'll spell it, equilibrium reaction with temp, meaning change in temp, change in concentration, or change in pressure, the equilibrium will shift to relieve stress. Okay, that still is very scientific-y or teacher-y, right? Your words would probably be different. But basically, if we were to sum this up, is you can change temp, concentration, or pressure that will affect an equilibrium reaction. And then when we say that the equilibrium will shift to relieve stress, what we're really saying is the forward or reverse reaction, one of them, will speed up. One of them will speed up to relieve the stress. Which one? Well, it depends on the rules.